Okay, so today it's chapter 4.1 and 4.2. It's been a while, but here we are. So, well, I read this so long ago, I don't really remember much, but um, we're gonna talk about concurrency. Apparently, we're gonna talk about declarative concurrency.
It's kind of funny
And
that the quote is about parallel skiing, which obviously parallelism, right? Except parallel skiing is about, well, sliding on skis down a mountain where the skis are parallel to each other. That has nothing to do with concurrency.
yeah, well, we're gonna say the same. The result of the program is the same as whether or not it is concurrent. That's really nice, right? Because this means that you're gaining performance, but the predictability is still intact. So it's
Yeah,
too
declarative
deterministic.
concurrency. Yeah, declarative concurrency is something the book mentions this as well, but it should be more well known than it actually is. It's very nice. It has very good properties.
What is new? The result of the program can be calculated incrementally. If the input of a concrete program is given incrementally, then the program will calculate its output incrementally as well. So what this means is that if you have declarative variables that are blocking the execution of something, and when they are unblocked, when the input gets unblocked, the output will also get unblocked. And if they block again, the output blocks again, and we keep going like that.
Yeah, it's very nice.
We can make this concurrence by doing the generation and mapping with in their own threads. So this uses thread statement, which executes concurrently. What is the difference between concurrent sequential versions? The result of the calculation is the same in both cases. This. In sequential version, Jen calculates the whole list before map starts. The final result is displayed all at once when the calculation is complete after 1 second. In the concurrent version, Nmap both execute simultaneously, and then whenever one makes something more ready, like more full of the information, the other one can pick it up. So whenever gen adds an element to a list, map will immediately calculate its square. The result is displayed incrementally as the elements are generated one element each tenth of a second.
You know what the funny thing is this is essentially the same semantics as Unix pipes, although Unix pipes are restricted to binary streams, right?
I have no idea. But good to know. We will see that the deep reason why this form of concurrency is so simple is that programs have no observable determinism. A program in the declarative concurrent model always has this property. If the program does not try to bind the same variable to incompatible values. Another way to say it is that there are no race conditions in the declarative concurrent program. A race condition is just an observable non-deterministic behavior. Very classic, right? Very freaking
Yep.
classic. Um, okay, we can skip most of that. And let's go to the data-driven concurrent model. Now we add threads in a single instruction thread. A thread is simply an executing statement. So we have a single, yeah, we're gonna see this, but this is a single assignment store. So that's the main difference, right? So we have a single assignment store, but we have multiple semantic stacks. And I
Yeah.
guess, I don't remember, is the book gonna talk about processes? I think it will, right?
Well, a semantic stack is basically equivalent to a process in Erlang parlance, right?
No, I'm talking about um,
Oh,
Linux.
operate. Oh, operating system processes. It
Yeah.
mentions them, but I don't think it mentions them here specifically.
Okay. In one of like somewhere, I think this book does mention that. That the difference between threads and processes, like more generally speaking, the difference is that threads are sharing a memory region.
Yeah,
Uh,
processes become relevant when we get to the distributed computation model later on. Uh, because in principle, you could have a distributed model where, okay, you have two nodes, they are on the same machine but on different OS processes, right?
exactly. Exactly. As thread is simply an executed statement, a semantic stack. This is all we need to start programming with declarative concurrencies. As we'll see, adding threads to the declarative model keeps all the good properties of the model. We call the resulting model the data-driven concurrent model. The second step extends the model by adding execution order. We add triggers and a single execution by need. This adds the possibility to do demand-driven computation, which is also known as lazy execution. The second extension also keeps the good properties of the declarative model. We call the resulting model the demand-driven concurrent model, or the lazy one. So now the basic concept. So now let's go to interleaving. So let's try to dissect what interleaving means. So there are two viewpoints. The language viewpoint is the semantics of the language as seen by the programmer. From this viewpoint, the simplest assumption is to let the threads do the interleaving execution. In the actual execution, threads take turns doing computation steps. Computation steps do not overlap, so they are atomic. This makes reasoning about programs easier. The implementation viewpoint is how the multiple threads are actually implemented on a real computer. So this is more like how you should think about it, and this is how we make that happen.
Yep.
Essentially. If the system is implemented on a single processor, then the implementation could also do interleaving. So we're talking about quantum and round robin. Well, in the level of threads, that's not. I think that's not exactly the terminology used because round robin is more like process.
Round robin is a scheduling algorithm
Yeah,
where
yeah, but can we
basically
do that for threads? I never implemented those myself, so I don't know.
I don't see why not.
Okay, so you could do that. But if you have multiple cores, so then we can do real simultaneous computation. And then, yeah, this is very nice. We're gonna call about ordering. We're gonna talk about ordering. We will use interleaving semantics throughout the book. Wherever the parallel execution is, there is always at least one interleaving that is observationally equivalent to it. That is, if you observe the store during the execution, we can always find an interleaving execution that makes the store evolve in the same way. Another way to see the difference between sequential and concurrent execution is in terms of an order defined among all execution steps. So this is very nice. A causal order. For a given program, all computation steps form a partial order called the causal order. A computation step occurs before another step. If for all possible executions of the program, it happens before the other. Similarly, for a computation step that occurs after another step, sometimes a step is neither before nor after another step. In that case, we say that the two steps are concurrent.
Very fancy.
So essentially, if something has an ordering constraint with something else, then we say that they have a causal order, being that before or after. But if they don't have the constraint, then we say that they are concurrent. So we have
Yeah.
sequential execution, and then we have the partial order. Order within a thread, order between the threads. So this is a thread, and this is between them, and so on, and so on and so forth. Casual orders of sequential and concurrent executions.
Yeah. This is actually worth expanding a little bit. Basically, when you have one thread spawning another, right? Because the thread instruction is atomic, like all other instructions, that means that every instruction that comes before that instruction will necessarily happen before it, and everything that comes after in either thread will come after. So, like, there's no magical way to reorder things relative to that point, right?
Yeah,
Because that's what causes the second threads to exist, right?
is the first one. So the first one needs to come before it. In a sequential program, all computation steps are totally ordered. There are no concurrent steps. In a concurrent program, all computation steps of a given thread are totally ordered. The computation steps of the whole program form a partial order. Two steps in this partial order are casually ordered if the first binds identifiable variable x and the second needs the value of x. So it's what Marinho
Yeah,
said,
that's
right? So
yeah, that's the other case where spawning a thread and interacting with a data flow variable that is shared, right? Those are the two synchronization points, I guess you would say.
yeah, yeah, yeah. So we have examples there.
Hello, Uli.
Figure 4.3 gives an example that shows some of the possible executions corresponding to a particular causal order. So what does this mean? This means that if you take this on the left, what are the possible ways we can execute this program with the interleaving within threads, among threads, I guess. We always start with IA, then we can either go IB and then stop and then go do I1, so this path, this third path, and then do I2 and IC. Or after IB, we continue with IC and then we go to I1 and I2. So this is what we mean by possible executions. Here the causal order has two threads, T1 and T2, where T1 and T2 has two operations, and T2 has three operations. Four possible executions are shown. Each execution respects the causal order. All instructions that are related in the causal order are related in the same way in the execution. All instructions that are related in the causal order are related in the same way. So I guess
Yeah,
this means, go on, that the
yeah,
I1
basic.
always comes first before I2.
Yes, and IB always comes first before IC, although the relative order between the two threads is not really. There's no causality between them, so they can
Exactly.
interleave arbitrarily.
Yeah, so that's why we have this mesh here. Um, So then we have non-determinism. An execution is deterministic if there is an execution state in which there is a choice of what to do next, a choice which thread to reduce. Non-determinism appears naturally in concurrency. If there are several threads, then in each execution state the system has to choose which thread to execute next. For example, the example we saw above, in a declarative concurrent model, the non-determinism is not visible to the programmer. Um, and there's a gotcha here. If there are no unification failures, attempts to bind the same variable to incompatible partial values usually consider unification failure as a consequence of programmer error. So this is basically you wrote the program wrongly.
Yeah, if you try to bind the same variable twice with incompatible things, then that's considered to be a programmer error in the for the purposes of the declarative concurrency model.
Yeah, but that will create an artifact because it will make the non-determinism visible.
Yes, at that point we're firmly outside of the declarative concurrency model.
So there are two reasons for this. First, data flow variables can be bound to only one value. The known determinism affects only the exact moment when each binding takes place. It does not take effect the plain fact that the binding does take place. Second, any operation that needs the value of a variable has no choice but to wait until the variable is bound. If we allow operations that could choose whether to wait or not, then the known determinism would become visible. This makes perfect sense, right?
It does. Uh,
Uh,
and slight spoiler, we actually get an introduction of we actually get an instruction that does precisely that later on when we step outside of the declarative concurrency model.
well, because then we're gonna um, I guess drop the referential transparency, and then when that happens, we are just like, okay,
Yeah,
now,
yeah. At some point, we're gonna have full-blown mutable state. It's some point before that happens, we get introduced to this. Okay, here's how you program with explicit non-determinism, which is no longer declarative.
uh-huh. Uh, okay, so we also have a scheduler for threads. Uh, we say that the thread reduction in the declarative concurrent model is monotonic. A ready thread can be executed at any time. So this is very similar to scheduling a process.
Yeah, it's basically the same thing. The details are slightly different because there's less isolation because we're running. We have a shared single assignment store, right?
Hmm We say that the system is fair if it does not let any ready thread starve. All ready threads will eventually execute. So for the classic example of this is if you have a ready thread, but you have some priority system and the ready thread is low priority. So you have to do something to assure that eventually that ready thread, although low priority, will eventually be executed.
Yeah, especially when you can spawn more threads at any time as well, right?
And there is something important here. Fairness implies that a thread's execution does not depend on that of any other thread, unless the dependency is programmed explicitly. Why does fairness imply that?
Uh, because if the execution of a thread is dependent on the execution of a
They
different
are not
thread that,
ready.
that is not related to it, then you could, if you knew enough about the implementation details, manipulate the state of your threads deliberately so that the other one never runs.
Ah, okay. So you know that somebody else depends on you, and you go to lengths to know that they will never execute.
Yeah, like if you know that the scheduler is not fair and it depends on some kind of detail of the implementation, like say spawning other threads messes it up, for example, you could just spam spawn other threads and prevent the other ready threads from running.
I see what you say. You could also like, oh, this is a priority type scheduler. I can just line one give myself the maximum priority.
Uh, I mean, there are ways to make a priority system that's still fair, and actually the book
That's
goes into
true,
that a little bit.
but like I'm assuming a very naive implementation, right?
Yeah, you could make a naive priority system, which is actually not fair, and say, okay, if a high priority thread is available, a low priority one will never run, and you know
Exactly.
that because the implementation is naive, and you say, okay, in that case, I'm just gonna spawn a high priority thread that just loops forever, and suddenly low priority threads never run, even though there's no data dependency between them, right?
Exactly. I see. Okay, I see why fairness implies this. Thank you, Marie. We extend the abstract machine of section 2.4 by letting it execute with several semantic stacks instead of just one. Each semantic stack corresponds to the intuitive concept thread. All semantic stacks access the same store. So this is the real deal. This is the main difference from threads to processes is because they can share the same store. Because at the point that you have multiple stores and multiple semantic stacks, they are like they're really really independent. So this is one of the usual criteria to the differentiation between the two concepts is that the threads they need to share something. Threads
Yeah,
communicate through this shared store. We keep the concepts of single assignment, store, environment E, semantic statement, and semantic stack. We extend the concepts of execution state and computation taking into account multiple semantic stacks. As the execution state is a pair, where MST is a multi-set of semantic stacks, and sigma is a single assignment store. A multi-set is a set in which the same element can occur more than once. Yeah, we implemented this twice.
yeah, we
Uh,
did.
MST has to be a multi-set because we might have two different semantic stacks with identical contents. Two threads execute the same statements. Makes sense. A computation is a sequence of execution states starting from an initial state. So essentially, we just need to keep track of the multiple stacks, but we have a single store anyway. So I would say, yeah, we just need to keep. Well, I think we need to go through this step. So the initial execution state is this. So this is the statement. This is the stack. This is the multi-set. At each step, one runnable semantic stack st is selected from MST, leaving MST prime. We can just say that MST is equal to the ST of the selected runnable semantic stack and MST prime, in which the symbol denotes multi-set union. One computation step is then done in ST according to the semantics of chapter 2. The computation step for the full computation is then, so you're basically doing a union, right? So this is essentially just doing a fold that is a little bit more fancy.
Yeah, kinda. You pick a stack from the multiset. Um, you execute a step to update the semantic stack and also the store, right, which may interact with it. And then you just put that back, and then you select another stack to execute, and that's how you do interleaving in this model.
Yeah. The choice of which ST to select is done by the scheduler according to a well-defined set of rules, and called the scheduling algorithm. This algorithm is careful to make sure that good properties such as fairness hold. A real scheduler has to take much more than just fairness. We're going to discuss that today, apparently. If there are no runnable semantic stacks in MST, then the computation cannot continue. If OST and MST are terminated, then we see the computation terminates. If there is at least exists at least one suspended that cannot be reclaimed, then we see the computation blocks. Uh, cool. So more details about how the multi-set interacts in the VM, I should say. Um, so if you have a thread that is with its own separate environment, the, it turns like it becomes this thing, which is essentially like translating this plus to multi-set union and so on.
Yeah, basically, to spawn a thread, you just create a new semantic stack with the same environment, and you add it to the multiset together with the reduced. Uh, well, because the current thread that does the thread statement presumably has more stuff afterwards, so we have to add that as well. So that's why you do two unions there.
Wait, repeat that last part.
Okay, basically, when you have a thread and you're executing the thread statement inside of it,
Mm-hmm.
that needs to spawn another thread, so it actually needs to create a new semantic stack with the
Yes.
contents of the. Yeah. But it also, when you do that, you also advance the current thread, so you have to put that as well. And that's why you do two unions on the right hand side of that arrow.
Ah, I see. I see. I see. I see. I see. I see. A block semantic stack can be reclaimed if its activation condition depends on an. Oh, we're talking about memory management, right? If its activation condition depends on an unreachable variable. If that in that case, the semantic stack will never become runnable again, so removing it changes nothing during the execution. That makes sense. So now I have an example. So here we're declaring locally the B. The B will only receive a bind in the thread, and in the original thread we're actually using B to do something. We skip the initial computation steps and go directly to the situation where thread and if statements are each on the semantic stack. So this is what we have, where B is a variable in the store. So this is the store. There is just one semantic stack which contains two statements. After executing the thread, we get the one that the thread would generate and the one from the original first thread.
Yep.
And these are the semantic stacks. There are now two semantic stacks. The first, containing b equals true, is ready. The second, containing the if, is suspended because the condition is that b needs to be determined. The scheduler picks the ready thread. After executing one step, we get empty because we're done. And then the second, but now the single assignment store, which is one for both, has something in there, which is going to make these ready. And now we're going to be able to execute this. So that's what we do. Uh, okay, so let's actually read this. We will still have some time. Why we consider the data-driven concurrent model as a form of declarative programming. The basic principle is that the output of a declarative program should be a mathematical function of its input. Again, referential transparency, very classic. We've seen since chapter 3 that declarative in this book means it means uh, not pure but referentially transparent.
Yeah, because it involves binding data flow variables, right? Because that's how procedures communicate in the framework that this book uses. But it is referentially transparent anyways, because yeah, if the inputs are the same, the output will be the same,
Exactly.
assuming you don't step outside of the declarative model that we have been looking at so far.
The program executes with some input values, and when it terminates, it has returned some output values. The output values are functions of the input values. Um, and there are two important differences with functional programming. First, the inputs and outputs are not necessarily values since they can contain unbound variables. So that's one of the differences that we've seen, right? Because if you grab the declarative model and you remove data flow variables, you get Haskell, right?
Actually,
Or ML, I guess.
you get pure ML actually, because Haskell has laziness, right? Which is
Oh,
still a
I,
form
I
of
mean, I mean,
concurrency.
okay, that's true. I forgot about the laziness. My webcam seems kind of busted now, but whatever. Um, Let me actually try to remove and put it back. It doesn't seem like 60 FPS, but whatever. And second, execution might not terminate since the inputs can be streams that grow indefinitely. So this is what we are calling partial termination. So this is what he meant by the things going on incrementally. Uh, let us factor out indefinite growth. We represent the execution of a concurrent program as a series of stages, where each stage has a natural ending. So this is a double function, which is essentially like grabbing a list and doubling up its inputs. And then this is the catch. The output stream contains the elements of the input stream multiplied by 2. As long as the input grows, the output also grows. The program never terminates. However, if the input stream stops growing, then the program will eventually terminate. So this is what we are calling partial termination. And then we also have logical equivalence. If the inputs are bound to some partial values, then the program will eventually end up in a partial termination, and the outputs will be bound to other partial values. But in what sense are the outputs functions of the inputs? Both inputs and outputs can contain unbound variables. For example, if you do this, then this will end up with this, where both inputs and outputs have unbound variables. Um, and then what do we mean by saying that the output is a function of the input? So let's see a simple definition for first principles. Before giving the definition, let me look at the two examples to get an understanding of what's going on. So we have this. Um, yeah, I think I have a question about this actually. So in the first case, the store ends up with x equal to 1 and y equals to x. So yeah, this is my question to you, Marinho. So when we say um, like this, what exactly are we talking about? You're talking about the store, but we know that the value of y is 1, right? If I ask it in the REPL immediately afterwards.
Yeah, right. Because you bound two variables to one variable to another, and the other variable was already bound, then the second variable is also bound.
Yeah, so this is strictly speaking about, like, it is counting the indirection that will happen in the store because y will 100% have two arrows, one going to x and x going to 1.
Yeah.
And in the second case, it's not doing that because y comes
Yeah,
first.
yeah, because if you bind two variables together and they are both unbound, the way Oz works, as described by the book, it creates an equivalent set between the two, including the two variables, right? It may have more than two variables. You can say A equals B equals C, right? Whatever.
Hmm.
But
Okay.
when you bind any variable in that set, it actually binds all of them to the
Yeah.
value.
Okay, so that's why he makes this, because I felt this very pedantic. I was like, yeah, he even admits that in both cases they end up being one, so what gives? But now let's see the second example. In both cases, X is bound to the same record, right? So full. Except that the first argument can be different, Y or Z. Since Y equals Z, we again expect the store contents to be the same for both cases. Okay. Now let's define what logical equivalence means. We will define logical equivalence in terms of store variables. The above examples use identifiers, but that was just so that we could execute them. A set of store bindings, like each of the four cases given above, is called a constraint. For each variable x and constraint c, we define values to be the set of all possible values x can have given that c holds. So true constraints c1 and c2 are logically equivalent if they contain the same variables, and for each variable x, the values. Okay, so logically equivalent means that at the end of the day you are the same.
Yeah, basically.
Okay. Uh, Deconstraint this and saying that y is equal to z is logically equivalent to this because y equals z forces y and z to have the same set of possible values, so that full yw defines the same set of values as full zw. Note that variables in an equivalent set always have the same set of possible values. Yeah, so I don't know if all this text was necessary, but this is very clear to me. Now we can define what it means for a concurrent program to be declarative. In general, a concurrent program have many possible executions. The thread, yeah, but they are logically equivalent. Now that we have this definition, we can just say that.
Yeah, that's what we were building up to.
The thread example given above has at least two, depending on the order in which the bindings x1 and yx are done. The key insight is that all these executions have to end up with the same result, but the same does not mean that each variable has to be bound to the same thing. Well, not directly, but indirectly they must.
Yeah, logical equivalence, basically. Well, it just
Uh,
says that in the next sentence.
a concurrent program is declarative if the following holds for all possible inputs. All executions with a given set of inputs have one of two results. They all do not terminate, or they all eventually reach partial termination and give results that are logically equivalent. And there is another way to say this is that there is no observable non-determinism. This definition is valid for eager as well as lazy execution. What's more, when we introduce non-declarative models, we will use this definition as a criterion. If part of a non-declarative model obeys the definition, we consider it as declarative for the rest of the program. We can prove that the data-driven concurrent model is declarative according to the definition, but even more general declarative models exist. The demand-driven concurrent model is also declarative. This model is quite general. It has threads that can do both eager and lazy execution. The fact that it's declarative is astonishing. A failure just means that abnormal termination happened. Multiple binds, for example. The program cannot terminate because there is no correct value of x. Makes perfect sense. If a declarative concurrent model results in failure for a given set of inputs, then all possible executions with those inputs will result in failure. Of course, because they are logically equivalent, which
Yep.
means that if one is classified as failure, everybody is classified as failure. We will see that all executions will eventually reach a conflicting binding and subsequently terminate, because you are saying that x is equal to two separate things. But those are skew issues. That's true. It is rather drastic to terminate the whole program because of a single programmer error. Often we would like to continue execution instead of terminating, perhaps to repair the error. A natural way to do this is by using exceptions. At the point where a failure would occur, we raise an exception instead of terminating. The program can catch the exception and continue executing. Um,
Yeah, this last paragraph here at the top of the page.
it is important to realize that execution after raising the exception is no longer declarative. This is because the store contents are not always the same in all executions, because sometimes you will enter an exception and sometimes you won't. So now there is an observable non-deterministic piece there.
Actually, to be more precise, you can reach an exception from different execution orders, and the store state will be different depending on the execution
That's
order
also
that
another
you took.
case. That's also another case. In the example above, because just before failure occurs, there are three possibilities of values. If the program continues execution, then we can observe these values. This is observable non-determinism. We have left the promised land. From the instance when the exception is raised, the execution is no longer part of the declarative model, but it's part of a more general non-declarative model. So uh, as we are building up the models, we are getting more stuff available, but less constraints.
It becomes harder and harder to reason about it. Yeah,
Which is kind of funny if you think about it, because you would think that then the book would start static typed and then go to dynamic type, because that's more power, essentially, but you have less constraints. So maybe there is an extension that could be done in the book about that. That's funny.
I mean that's not quite the same thing because if you think about it, dependent types are static, but they are very very powerful.
No, 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 but yeah, but that requires, how should I say this? They are more powerful and they are static, but they require a lot more. That's something still in development, I would say. That's really not. I wouldn't say bleeding edge, but I would also not. I would say very non-mainstream. I would say that.
That's
Uh,
fair.
because, for example, if you try to if you're trying to type down the Y Combinator in a dynamic language, it's way easier than a static one for many different reasons. So, in my opinion, that's actually an advantage because you can write more powerful stuff more easily. But at the same time, like it's it's what Nathan said, constraint-based programming, in the sense that you want to constrain yourself. It's a very non-intuitive idea that
Don't use that term, Lemos, because it will come up later in the book and people will be confused when they watch the videos because you're using the same
wait,
term to mean something else.
wait, the book actually talks about constraint-based programming? Are you kidding me?
It does, yes.
Um, okay, but Nathan is already coined that term anyway. So
Yeah,
uh,
he's late to the party. That term is already taken, unfortunately.
so is the fact that you want to constrain yourself because you understand that having more power open more potential black holes, essentially. But this is a very not new idea. It's just new to people that are like, I don't know, probably doing JavaScript all day.
With great power comes great responsibility.
Exactly.
Yeah, Spider-Man should be required reading for anybody doing programming.
Oh man, only have 2 minutes. Oh, but we are halfway, so let's speed this up. Okay, so failure confinement. This is essentially okay. So this is actually pretty cool because this is essentially getting out of the declarative model because you are introducing threads. Well, not threads, exceptions, but we are making sure that we have a catch if you like to go back in.
Yeah, this is basically saying, okay, things can go wrong in this block, but if they do, we handle them in such a way that when we leave the block, we are back in declarative land.
Yeah. And this is the responsibility of the programmer to go back. For the reader who is curious how to do this, well, we have an example here where we are doing exceptions, but after we detect later if we had an error before, and then if we did, we just rearrange the pieces. Um, Two things have to be repaired. First, we catch the failure exception with a try, so the execution was not, so we're not going to blow up. A try statement is needed for each binding since each binding could fail. Second, we do the bindings in local variables, which are invisible to the rest of the program. We make the bindings global only when we are sure that there is no failure. So yeah, basic thread programming techniques. So let's go. So a thread statement creates a new thread. So this is, we've seen this before. This creates a new thread that runs concurrently with the main thread. And this is just syntax sugar for this other thing. Oh, it's because we are using a thread as an expression. So this
Yeah.
needs to be essentially like this, nothing new. Then a new data flow variable is created to communicate between the main thread and a new thread. When a thread has no more statements to execute, then it terminates. Each non-terminated thread that is not suspended will eventually be run. We say our schedule is fair. Thread execution is implemented preemptively, which means that we will interrupt them. Uh, each thread will get the processor time and discrete times called time slices. It is not possible for one thread to take over all the processor time. This is actually not what preemptive means. Saying that it will be executed before a time slice is part of the definition, but as far as I know, preemptive means that you will be interrupted.
Which is the same thing as being given a time slice, because if you don't have an explicit time slice, you just run until you get blocked, right? Which is essentially just cooperative scheduling.
It is cooperative scheduling, what you said, but I feel that it's, I don't know. I would put the interruption portion or corollary in here because to me that's like the essence of preemption. It's the fact that you are doing your stuff and I don't care. I will stop
How rude.
you. Yeah, I don't care. Your time is done. I'm gonna interrupt you. So we have the browser that works well in a concurrent environment. In what orders are the values displayed? And then the answer is either one. Is it possible that something like this will be displayed or worse that the browser will eventually behave erroneously? At first glance, it might seem so, since the browser has to execute many statements to display each value. Um, but the browser is designed for a concurrent environment. It will never display strange interleavings. So it will treat these as atomic, I guess.
Yeah.
Each browser can give its own part of the browser window to display its argument. If the argument contains an unbound variable that is bound later, then the display will be updated when the variable is bound. In this way, the browser will correctly display even multiple streams that grow concurrently. So this is what we have, and this correctly displays the two streams. So we spawn these two threads, they keep hanging there, and we keep binding things. So um, we're gonna display all roads and all rooms. And then we're gonna have this, and so on and so forth. Data flow computation with threads. So now we are using the data flow variables and threads together. We have a simple calculation, which is essentially displaying. What is this displaying? This is displaying. Oh, actually, we are holding. We have unbound variables in here.
Yeah.
So then we display. We want to display the outputs and then complete it. If you feed this program in the browser and display all the variables as being bound, observe what happens when you input the following statements one at a time. It will display them incrementally. Use an declarative program in a concurrent setting. So we have the for all procedure that we did before. We put that in a thread. If L is bound, this will we immediately suspend it. If we combine L in other threads, this is going to also be done incrementally because L1 is being bound later, and then L2 is being bound even more later.
Yep.
Yeah, again, nothing too crazy. Actually, in this setting, it kind of makes data flow variables feel more like normie, imperative-like synchronization mechanisms.
Look at the concurrent map that's in the next paragraph.
Here's a concurrent version of map. So we have a function map, and then we are threading the execution of every single each element in a separate thread, and in the main thread we are doing the tail call.
Yeah.
So this is how it looks like. So pa, so like boom, boom, boom. Running thread, create new thread, synchronize on the result. The thread
Yeah,
statement is used here as an expression. Go on.
no, you're right. Like the way data flow variables interact with threads, it's very natural.
Yeah. Uh, okay, what else? So then we have an example how to use that in the browser. Um, creating two threads for the first two arguments. Yeah, this is creating a bajillion threads, right?
Yeah, one for each item of the list. Yeah, of the string, I should say.
Exactly. We'll create a thread and terminate the computation of the main. The three threads will also terminate, resulting in the final list. Remark that the result is the same as the sequential map function, only it can be obtained incrementally if the input is given incrementally. Actually, what if we give it incrementally, but it's not concurrent?
How would you do that?
You pass an XS that has an unbound variable in the tail.
Well, the call to map is going to block in that case.
Back.
Yeah, the call to map would block in that case. You would have to either put the call to map in a separate thread or well, bind the variable in a separate thread, I guess.
Bind the variable in a separate. No, but if you have no multi-threads, like if you're just doing like fx here, I think this would blow up.
Why?
Well, not blow up. It
It's gonna
would.
block.
It's gonna block. Yeah, it's exactly. It's gonna immediately block, because this will not be able to do the case on it.
Yeah.
Um, cool. Uh, then the main thread will traverse the list. Blah blah blah. Concurrent Fibonacci function. So we are calculating the recursive, one of the recursive calls with threads. A total 8 threads are involved in this calculation. You can use this program to test how many threads it will be used. Data flow and rubber bands. By now it's clear that any declarative program can be made concurrent. Yes. Because each data flow variable will be bound to the same value as before, the final result of the concurrent version will be exactly the same as the original. One way to see this intuitively is by means of rubber bands. Each data flow variable has its own rubber band. On end of each of the rubber band is attached where the variable is bound and where the other the other end to where the variable is used. Figure 4.7 shows this. Yeah, exactly. I guess this is fair to say. In the sequential model, binding and using are usually close to each other, so the rubber bands do not stretch much. In the concurrent model, binding and using can be done in different threads, so the rubber band is stretched. The user always sees the right value. Chip concurrency and program structure. What is this talking about?
The fact that Java threads kind of suck.
Threads are so cheap that one can afford to create them in large numbers. For example, entry-level personal computers of the year 2000 can support more than 100,000 simultaneous active threads. If using concurrency lets your program have a simple structure, then use it without hesitation. But keep in mind that even though threads are cheap, sequential programs are even cheaper. Um, Yeah, you should create threads only when the program needs them. Yeah, this is like you could do it, but that makes life easier to harder to think about. So only do it if you have to do it. You
And
should
if you
ever.
have to do it, just do it because they are cheap. Yeah. Unlike Java, where
Oh,
threads
I,
are
I also
expensive.
would say that it's not about being cheap. Like being cheap is nice, but that's not the main reason. The main reason is because they are awesome in this case.
Yeah,
Um, we have seen. Okay, this is now talking about fairness again, as we had the spoiler earlier today. Round robin. Okay, so it does talk about it. I was not crazy.
it does. Yeah,
Um, it would be inefficient to let each thread execute only one computation step before putting it back in the queue. So yeah, time slice or quantum, which is the amount of time you have before getting interrupted on your face. And this, yeah, stopping a running thread is the preemption. That's what I was talking about. That's what I was missing. This is like, you're done. It's over.
how
Uh,
rude.
the first way is to count computation steps is to give them the same number to each thread. The second way is to use a harder timer. The counting approach has the advantage that scheduled execution is deterministic. Running the same program twice will preempt threads exactly the same instance. A deterministic scheduler is often used for hard real-time applications where guarantees must be given on timings. The timer approach is more efficient because the timer is supported by hardware. However, the scheduler is no longer deterministic. Any event in the operating system, a disk or network operation, will change this exact instance. This is obvious, right? Because if you're using, I don't know, at this level, I think even using a worse cable matters.
Yeah,
So you don't have the deterministic portion of that anymore. But of course, the Mozart system uses a hardware timer.
I mean,
Uh,
it's not a hard real-time language, so we could just use the more efficient approach, even if it's not deterministic.
that is fair to say. Priority levels. For many applications, control is needed over how processor time is shared between threads. For example, during the course of a computation, an event may happen that requires urgent treatment. On the other hand, it should not be possible for urgent computations to starve normal executions to cause them to slow down, not ordinarily. A compromise to seem to occur well in practice is priority levels, which is the same as priority for processes, as far as I can tell. Uh, but the difference is that these priorities matter for the thread scheduler, and the processes they matter for the OS scheduler. Within each priority level, threads share the processor time fairly as before. The Moser system uses this technique. It has three priority levels: high, medium, and actually I like this way of doing priority because like processors divide among the priorities of this is in talks about in ratios, not on like simple integers. So we have 100 for high, 10 for medium, and 1 for low, which are percentages of time that you are guaranteeing for each group. So that's
Uh, yeah,
great.
it's yeah, it's basically well, it explains here, right? If you take the number of the priority and divide by the sum of all of them, which is the total number of well, the total number used in this ratio, then you get a fraction which says how much time you get available for each priority level.
Exactly. So 90%, 9%, 1%. These percentages are guaranteed lower bounds. If there are fewer threads, then they might be higher. For example, if there are no high priority threads, then the median thread can get up to 10/11th of the processor time. And this can be changed by the property module. And then we also have the child thread management, which is like when a thread spawns another thread, what should we do? If the child of a high priority thread would have say medium priority, then there is a short window of time during which the child thread is medium priority until the parent or child can change the thread's priority. The existence of this window would be enough to keep the child thread from being scheduled for many time slices. This could result in hard to trace timing bugs. Therefore, a child thread should never get a lower priority than its parent. Yeah, so this is talking about um, the existence of a window of time that is required for us to change it back, to change a child thread to something more easier to deal with, that creates a race condition.
Potentially, yeah.
And that's a problem, so we rather not do that. And this is a very classic problem. Like, if you pick a classic OS normie book in C, it will talk about this problem.
Yeah, if you go into language implementation at the depth that this book goes, inevitably there is a lot of overlap with operating system concepts.
Because this is essentially talking about that if the quantum is too small, we are wasting time doing the context swap. But if they are too long, somebody may starve to death.
Yeah.
So that's essentially the problem, and that's not good. That's not good at all. Um, what is needed is a hard real-time computing system, which is a special kind of hardware to get with special kind of operating system. But this is not in the scope of this book. Uh,
Yeah, that paragraph is talking about what if you have a bunch of threads and they all interact with the real world independently, right?
oh, I see. And then we have cooperative and competitive concurrency. So cooperative concurrency is for entities that are working together on the same global goal. Threads support this. Any thread can change the time ratios between the three parties, as we'll see. Threads are intended for applications that run in an environment where all parts trust one another. On the other hand, we have competitive concurrency, which are for threads that have local goal. They are interested only in their own performance, not the global performance. Competitive concurrency is usually managed by the operating system in terms of concept called a process. Yeah, so it does talk about processes. I was not crazy. Um, this means that computations often have a two-level structure, which is this, right? So we have threads, and we have a more something that is wrapping the threads, which is called a process. And on the
Yep.
level of process, they are competing among each other. But on the level of threads, they are cooperating among each other. Processes are usually owned by different applications with different, perhaps conflicting goals. Within each process, there is a set of threads interacting with each other doing cooperative concurrency. Threads is in one process are usually owned by the same application. Competitive concurrency is supported by Mozart by its distributed computation model and by the remote module. Um, I guess that's fair to say that okay, if you're doing competitive stuff, it yeah, it can be seen as a distributed. I guess that makes
I
sense.
mean, as soon as you reach that level of isolation, then the fact that you are running on the same machine is kind of incidental, right?
It's because I don't see distributed models as competitive because they maybe the competition is generating something that is the global goal of the distributed thing, right?
But
So
each process is still competitive with the other ones
no, but
locally.
yeah, but their competition is still generating something forward for a global goal, right? So, for example, if you have to synchronize processes because I don't know of a database management, the owner of this distributed system wants the database to be synchronized. So
Oh, but you are assuming that there's only one owner.
no, maybe there are multiple owners, but they all want the same thing.
Are you sure?
Well, if you have a distributed system with multiple owners in a company, for example, I would imagine that everybody
Oh,
wants.
but you are assuming that there is a single company that owns everything.
Okay, so we are not talking about only distributed. We are talking about decentralized. Like
Yeah.
ownership is actually like I don't know, I guess a blockchain system where they don't know each other at all and there are multiple entities interacting with the thing and they have conflicting goals. So the distributed and decentralized portion of the system now is different. But if I have, for example, an Erlang server with multiple nodes across the globe, yes, I am the owner, the only owner of this system, although it is distributed. Do you agree with
Yeah,
that?
I agree with that.
So in this sense, I would say that if they are talking about what you were talking about, I think decentralized is a better word for that.
I mean, theoretically, the module is kind of agnostic, right? It doesn't care if it's centralized or decentralized. It's just that there are multiple processes potentially on different machines and they interact with each other.
That's fair. This is relatively easy to program because the distributed model is network transparent. The same program can run with different distribution structures and different sets of processes, and it will always give the same result. And
Assuming,
finally,
of course, that no process fails. Important
yes, yes, yes,
caveat,
yes.
right?
Assuming no skill issue.
No, 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 not
Uh,
skill issue, because there could be a hardware failure, right? That's outside of your control.
oh, okay. That's also fair, but is that mentioned in here and I just missed it?
Yeah, it's the footnote. This is true as long as no process
No, but this
fails.
is a skill issue. I'm
No,
talking
no, no, a
about the
process.
the
A,
computer exploding.
no, no, it says as long as no process fails, but a process may fail because the network cuts out. It may fail because the computer exploded. It may fail because of a skill issue. That's true, but not only because of a skill issue. There could be many causes.
That's fair. That's fair. Um, yeah, that's I would say that's fair. Although the book doesn't mention this like hardware failures, it mentions programmer
It
failures.
actually, yeah, it goes into that on chapter 11. Partial failure, fault tolerance, all that good stuff.
Okay, we're very far from that. The module thread and property provide a number of operations pertinent to thread. Some of these operations are summarized. The the priority P can have three values. You have seen this before. This is just explaining how you can use the property module. Blah blah
And
blah.
yeah,
And
and you can change the ratios between the time slices for the different
can you change
priority
the
levels.
scheduling algorithm?
I don't think so.
Why?
That would lead to more complication because you would have to implement the schedule algorithm either as something that can be implemented in the user lane of Mozart or of Oz, or you'd have to have multiple ones baked into the runtime and have some means of selecting between them.
This is a dynamic language. Why can't we just uh, they can just provide an API. So like make a function or a procedure with this amount of arguments, and this is what it needs to be, and this needs to be the output, and everything in between is yours, is your you to care about.
They definitely could, and it would not surprise me at all if there was some Lisp system of old that did that precisely that. But yeah, I'm not sure if Oz, if Mozart specifically does that.
But that's surprising that you cannot change it. Like for a language that for something that is attempting to do the small talk trick, the fact that I cannot just like they have menus and changing the priorities, like it's not consistent with the philosophy of this that you cannot change that. Weird, but okay. And then that's it. That's what we have for today because we today is only 4.1, 4.2. So let's settle for the next time, which I want to be next Sunday because I want to go back to reading this. So let's see, 4.3. How many pages for lazy execution? Jesus Christ. Okay, so it's like 30 pages only on laziness. Uh, so this is 26 pages, but this is only 20 pages. Okay, so we either go low or too huge. Too low or too huge. What you rather do, Marinho?
I think it would not be wise to include lazy execution together with strings because strings actually goes kind of in depth. Um, I I'm thinking we should do 4.3 and 4.4. I think that's reasonable.
Okay, so that's settled. I'm gonna finish the recording now.